Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions, equilibrium of a body and Archimedes upthrust. This exercise was a previous one in the brief exams in 2003 first session, third exercise. The title of this exercise is a pure metal or alloy, and here by alloy they mean combination of metals. So consider a metallic solid S that bears the inscriptions 100% copper, 8900 kilogram per meter cube. So here, what is meant by these inscriptions? So 100% copper means that the solid S is completely made up of copper. Now 8900 kilogram per meter cube, what does this quantity represent? We can determine this quantity from its unit. So its unit is given by kilogram per meter cube, and knowing that kilogram per meter cube is the unit of density. So here this density refers to the copper. So they are claiming that the density of the solid S is completely 809 or it's equal to 8900 kilogram per meter cube, which means that it's 100% made up of copper. In order to check whether the inscription about the density is true or not, we perform the following experiments. Part A, first experiment. In order to determine the mass of S, we suspend it from spring balance by means of a thin string. So they mentioned figure 1. Now we can use it. Notice that they didn't mention figure 2. We are not allowed to use it. So here we have the solid S connected from the free end of the spring balance by means of a thin string. This is the string. Okay, the solid S takes then an equilibrium position, so it is at equilibrium under the action of two forces. Part 1. Give the name of these forces. So for sure the solid has a mass, then it will be directly subjected to the weight. So one of the forces is the weight. Here, because we have a string, then the other force is the tension along the string. Then the forces are given by the weight vector W and the tension along the string, tension T. Now, number 2, give the relation between these two forces, and here by the relation they mean the vector relation or the condition of equilibrium. Then how do you apply this condition? We always start as a title by writing at equilibrium. Always on the left we write the sum of forces acting on the solid S, and they are given by the weight W and the tension T. And on the other side we write the zero vector corresponding for the equilibrium. We don't forget the vector over the zero because this is a vector relation. Now moving T to the right hand side, we'll have that the W vector is equal to minus T vector. So what does the first equation tells us? That both forces acting on the solid S, the effect of these forces cancel each other in order to give us the condition of equilibrium, which is the zero vector. And the other equation tells us that both forces have the same line of action. The minus sign is for the opposite direction and same magnitude. Now in number 3, referring to the reading of the spring balance of figure 1, give the value of the weight of S. So here, what does this weight represent? The real weight or the apparent weight? Because they didn't mention that we have a liquid, so we consider that this weight is the real weight. So this is the real weight. Now referring to the reading of the spring balance, because the spring balance, the solid S is at equilibrium in air, then the spring balance indicates the real weight. Then let's justify, since the suspended object which is given by S is in air, as we can see from this document or from this figure at equilibrium. Then the spring balance indicate its real weight. Then the real weight here, which is denoted by W, let's say, is equal to the indication of the spring balance, which is given by 8, And because we are taking data from the spring balance, we multiply by the scale, which is given by 1. So the weight is given by 8. Since the scale is expressed in newtons, so the value of W will be in newtons. Then the real weight, which is denoted by W, is given by 8 newtons. So here W doesn't have a subscript R, it's okay. Now in number 4, calculate the mass m of the solid S. Take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on Earth. We know that the weight, the real weight, and the mass are related via the following formula. We are interested in determining the value of m. So constructing the triangle of this formula here, because we have multiplied, and W will be at the top, m and G at the bottom. Putting our hand over m, then m will be given by W divided by G. The value of W is given by 8, the value of G is given by 10. Plugging this fraction in the calculator, the value of m is given by 0.8. Since everything is expressed in the SI, then the value of m will be in the SI, which is kilograms. Then the mass of this metallic solid S is given by 0.8 kilograms. Then from the first experiment, what we deduce from the first experiment, the mass of this solid is given by 0.8 kilogram. Yet the aim of this exercise is to determine the density of this solid, so we expect from the second experiment to determine the volume of this solid. Now let's move to the second experiment, which is part B. Now, second experiment, solid S kept suspended from the spring balance is immersed in a test tube containing water of density 1000 kg per meter cube. Then the density of water, so let's say density rho W is given by 1000 kg per meter cube. And they mentioned figure 2, then now we can use figure 2. The reading of the spring balance changes. Okay, number 1, reading the indication of the spring balance give the value of the apparent weight W weight of S. So here, let's first justify, because the solid S is immersed in a liquid, for sure it is at equilibrium, then the spring balance will indicate the apparent weight. So we are in number 1, since the suspended object is immersed in a liquid, for sure at equilibrium, then the spring balance indicates its apparent weight. Then in this case, the apparent weight is given by the indication of the spring balance, which is given by 7. And because we are taking, data from the spring balance, we multiply by the scale, which is given by 1. Then the value of W apparent is given by 7. Since the spring balance is expressed in newtons, so the value of W apparent will be expressed in newtons. So the apparent weight is given by 7 newtons. Now here, let me write that the real weight is given by 8 newtons. And the apparent weight is given by 7 newtons. Now in number 2, give the name of the force that led to a different indication on the spring balance and calculate its value. So here, because we have a liquid, then as it will be directly subjected to Archimedes' upthrust force F, and this is the force behind the reason or due to the difference in the indication of the spring balance. Then let's say that the name of this force is Archimedes' upthrust force, F upthrust vector. And in the same part they are telling me and calculate its value, and here by calculate its value they are asking me about the magnitude of F upthrust, which is the fourth property of the Pilldom. We know that F upthrust by definition is given by the real weight, which is denoted by W minus the apparent weight. Now the value of the real weight is given by 8, and the value of the apparent weight is given by 7. So the value of F upthrust is given by 1. Since both the real weight and the apparent weight are expressed in newtons, the value of F upthrust will be in newtons. Then we have that F upthrust is equal to 1 in Newton. Now in number 3, calculate the volume of the displaced water, deduce the volume V of S. Let me make some space here. So they are asking me to calculate the volume of the displaced water. So what does the volume of the displaced water represent? It's the same as the volume of the, it's the same as the immersed volume. We know that the immersed volume and the magnitude of F vector, which is the Archimedes upthrust, are related via the following formula, that F upthrust is equal to the density of the liquid times the volume of the immersed volume times G. Knowing that we are interested in determining VI, constructing the triangle of this formula, here because we have multiplied and F upthrust will be at the top, rho L VI and G at the bottom, we are interested in determining the value of VI, which is given by the value of F upthrust divided by the density of liquid, which is denoted by rho water, multiplied by the value of G. The value of F is given by 1, the value of rho in the SI is given by 1000, the value of G is given by 10. Plugging this fraction on the calculator, then the volume VI is given by 1 times 10 to the power minus 4. Since everything is expressed in the SI, so the volume VI will be in the SI, which is meter cube. Then VI is given by 1 times 10 to the power minus 4 meter cube. So this is the answer to the first part of number 3. Now in the same part they are telling me to deduce the volume V of S. So notice that this volume represents the volume of the immersed part. But here, as we can see from figure 2, that the solid S is completely immersed in the liquid. So this is the volume of the immersed part, the shaded volume. So because S is completely immersed in this liquid, VI is equal to V. Then let's say here, since S is completely immersed in the liquid, and in this case the liquid represents the water, then in this case the volume V of the solid S is equal to VI is equal to 1 times 10 to the power minus 4 meter cube. So usually they give half a mark for this statement. So in this case the volume of the solid is given by 1 times 10 to the power minus 4 meter cube. This is meter cube. Now let's write here that the volume V is given by 1 times 10 to the power minus 4 meter cube. Now part C, the conclusion, part 1, deduce the density of the substance of S. And here notice that deduce, it means that we need to use the previous part. There is no previous part in this part C, which means that we need to use the results of both experiments, second experiment and in the first experiment. In the second experiment we have determined the volume V, whereas in the first experiment we have determined the mass. Then we can determine rho of the solid S using the formula mass over volume. So the mass is given by 0.8 and the volume V is given by 1 times 10 to the power minus 4. Plugging this on the calculator, the density is given by 8000. Since both M and V are in the SI, so the value of rho will be in the SI, which is kilograms per meter cube. Then the density of this metallic solid S is given by 8000 kilogram per meter cube. Now number 2 is the inscription about the density of S, true or false. Why? In order to know or to determine whether this inscription are true or no, it is sufficient to compare the calculated density with the given density of the given inscription. Knowing that the value rho that we have calculated is given by 1000 kilogram per meter cube, whereas the inscription holds the following value, 8900. So because by comparing both densities, we can see that the given density is not equal to 8900 kilogram per meter cube, which means that the inscription is false, is not true. Then here we are in part 2 of part C. Let's say since the density of S is not equal to the density of the inscription of the inscriptions, because we have two inscriptions. In other words, 8000 kilogram per meter cube is different than 8900 kilogram. Let me write it here. Then the inscription is false. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon on another one.